are based on hardware support for stacks. If you guys recall, the data structure is a last in, first out data structure, and there's a register that keeps track of the top of the stack, right? We talked about all this stuff when we were talking about L3. It works like almost exactly the same way, except there's built-in hardware and a register hardwired to keep track of the stack. It's going to get placed somewhere in the memory that we don't handle. It's the operating system that assigns the location of the stack. All we care about is the top of the stack, and then based on that, we can calculate where items are when we place them on the stack, okay? So to push, it's the same thing. You first decrement the address of the stack, and then you put the item on top. When you pop, you increment. You pop the item, and then you increment the address to move the top of the stack. Okay, that's what we talked about. In the version of x86 that we're learning, because it's a 64-bit system, they changed the way things work. Back when it was 32-bit systems that were dominating the market, they had a lot of legacy support for the old ways of doing things. So they allowed the stacks to kind of get out of alignment from the actual default architecture. They don't allow stuff that's outside of 64-bit or 8-byte operations anymore. So everything is quad words only. So as you can see, when you decrement and increment the addresses, it goes by 8. Okay, because we are pushing 64-bit entities on there only. Here's an example of how this would look like. Here's your empty memory. The left side is the addresses. So one word about visualizing memory. You have to draw a table and kind of visualize it that way. Because if you try to do it all in your head, it's near impossible to do this, right? So I always recommend making drawings. And then when you do computer science discussions, it's a standard thing to kind of draw the memory map. Here is a way to draw a memory that has the addresses in a certain order. So which part of the table is a higher address and which part is the lower address?
Higher is on top.
Yeah.
Higher is on top, lower is on the bottom in this case. All the stuff that we've been doing so far, where was the lower address? And where was the higher address?
Me.
I had the low address at the top, like it started at 0 and you go up this way, right? In this diagram, we're drawing it flipped upside down. Both are used depending on what you're trying to do. So the reason I had the stuff before where the low address was at the top and then the address grew as we came down was because we were putting in instructions inside the memory, right? So like line 1 of your code, line 2 of your code is sitting in the memory in the order that they should appear, right? So it was more natural to look at it this way. Does that make sense? And a lot of times you'll see that. When they talk about stacks, they will do it this way and flip it like this. Okay, yes?
So they'll do it and then flip it so it's back up. So the lower address is like where it was when we were doing before.
It's opposite of what we were doing.
Yeah.
But because you'll see the address written down,
Yeah.
it should not confuse you at all, right? Because you know which one's lower, which one's higher. Okay? So it's used both ways. Sometimes for the same problem, they'll draw 2 tables. One is going this way, one's going the other way. And you have to be able to work with it. Okay? Yes?
So why is the stack opposite? Is it because the architecture? Is it because?
This is just the standard way of
Okay.
drawing the stack diagram when we do stacks in memory.
Okay.
And as you set up what we call frames that we'll talk about. So let's see how it works, okay?
Okay.
So in the beginning, the stack is empty. And so my pointer to the top of the stack, the RSP register, will tell you that it's at location X
X100.
1000, right? All right. This is not 1000, okay? So kind of make sure you distinguish between decimal numbers and hex numbers. This is a hex number. Okay. When you go to insert an item, so here comes, when you push, 64 bits worth, right, of
Mhm.
data that represents the value 1 onto the stack, it's going to first decrement, right, the top
Mhm.
counter, so
Yeah.
it goes down, and then you insert it into that position.
Mm-hmm.
What is sitting at the previous location here?
Okay.
Nothing. And that's the way stacks work. Whatever you start a stack of certain sizes, the very top location, initial location you started with,
Mhm.
will remain empty.
Mhm.
Okay? You push another item, this is what happens. Where's the top now?
It's
At 1.
No,
X
the top is at X.
0,
zero,
F, F0 is the top. So if I say, hey, grab the item from the top of the stack, we go here, and this is what we get, right? Does that make sense?
Yeah.
So stacks grow this way,
Down.
this way. That's the standard convention that we use for stacks. And then here's an example of pushing another one on there, right?
Mhm.
And so forth. Well, the opposite of the push is the pop operation. And for the pop operation, let's say this was the situation we had, and we asked the computer, hey, pop off the item from the stack, put it in the RAX register. The computer's gonna take this thing, copy it over to RAX, and then it's going to take the RST pointer, the top pointer, and move it up, right? Add 8 to it. So this is what we end up getting. So now if I ask you, what's at the top of the stack? What is it?
Is it the position?
This thing, right? What about this?
This is gone. It's lost.
Well, we popped it off
Yeah.
and put it in RAX and used the value. Is it physically gone?
No. No.
It's still there, but it's not part of the stack anymore though. As soon as I push another item onto this stack, it would overwrite this thing and put it there. Does that make sense?
Yeah.
And if you pop off from here, this is wrong. Not wrong, but it's in the wrong place. Should have been like this, right? Yes.
So what is Rex? RAX in this equation?
What is RAX?
It's 5? No?
What's gonna be in RX
RX.
after you pop?
The address.
Yeah.
The top item stored at the top of the stack, which is this one, not the address.
Okay.
So 5.
And
Here,
then
our VX will have,
RX will have.
this was the top of the stack, and you asked it to pop off the stack.
Yeah.
That's not the question.
What is it?
It's. So. It's
If
3.
you pop from the stack,
3?
Three.
3?
Yeah.
Okay, so. Okay. Okay.
Yes.
Is it always making this work when you're working with stack, or would it be possible to have the low at the start and the high at the end?
For stacks, this is the convention. Always grows downward, so it's the reverse. So like high addresses show up at the top, low addresses show up at the bottom. If I didn't tell you that, would you not know it?
I mean.
What's it
You
at?
have to know it because the address is written there, right? There's never a time where I don't show you the address where you don't see the address with the table.
But then I would have to do conversion because recuerda que después estaba aquí, entonces I would to convert it to
The hex numbers, you gotta get used to the hex values. That's all I can say about that. Yes.
So is there a value making Rex 5 or Rex is just
Value what?
So RAX is there a value that makes it 5 or
What do you mean?
I
What
forgot.
is RAX?
RAX is well, R is 30.
It's a register.
Oh yeah.
RAX is a register. So we took this value from the memory and put it in the register.
Okay.
That's what that did.
And 5 is in that register right now.
What's that?
And 5 is in that register right now, or no?
Yeah, it is.
Okay.
Yeah. Yes.
What about RBX? Is it the same thing as REX?
What's RBX? It's another register,
Another.
right? What's gonna be there?
The
This is the situation we're in, right?
Mhm.
And then I'm calling pop.
It'll be 3.
Yeah, 3 in RDX. So as a result of this, we'll have 5 in RX and 3 in RDX, right?
Do you have to manually change the RSP? What's an RSP or does
Not
it-
if you're using the pop operation or the push operation.
Okay.
It's done, it's hardwired to do it for you automatically. Later on, we're gonna see
Okay.
cases where we manage the stack ourselves,
Okay.
in which case we have to manipulate the RSP values ourselves. Okay, so we'll see that, yeah.
How are you moving the 5 into RX? Like, what would be the command?
That
Using
pop,
No, I mean, to move 5 into RX.
pop,
No.
pop, RX. What's pop?
Pop.
It takes the top item from the stack.
Yeah.
Where does it put it?
Down.
Whatever,
Oh, so it's
where.
literally up or
Yep.
down.
That is the instruction. Yes.
For x86 registers, are you allowed to use any register you like?
Any register you like?
Yeah.
Yes, typically yes. They're all considered general purpose registers. Some of them are hardwired for certain things, right? Like the CX variants, RCX is a counter, right?
Yep.
And they're sometimes hardwired against certain instructions, so you gotta be careful.
Would
Oh.
RSP be one of them?
RSP is something that you should not use with anything other than stack operation. It's a stack point. That's what SP stands for, stack point. So you never use it for anything else other than stack point. Yes.
Does that also go for, was it the RBP? Like,
Which one?
I have to look back at the slides, but.
The
it wasn't-
BP?
Yeah, the BP.
It's the same thing,
where
it's used for-
dedicated towards stack
Stack,
operations.
yes.
Okay.
So the BP, RBP and RSP are both used to handle stacks.
Mm.
RBP is kind of deprecated, it's not, you don't have to use it. In 32-bit systems, the EDP version was exclusively used along with RSP whenever we called functions and stuff like that. We're gonna get to that in a second, but we're not gonna do it, so we will probably never touch RBP. There's no need to look at it. Any questions about the stack? Yes.
So just to be sure, pop racks takes the 5, doesn't delete it because it's still there.
Yeah.
Doesn't delete it.
It just copies it into our.
Yeah. It copies it to REX, and then after that, it gets pop. It moves. Does it move? Does it move it?
It moves the top.
Yeah, it moves the top.
Yeah, the address. It changes. the
Yeah.
address.
Yeah. Okay. There you go.
Question.
Yes.
So we're seeing like lots and lots of like operation and commands. What exactly do we need to know like without consulting material or anything like that? For like in terms of like the register.
We haven't seen lots and lots of commands actually.
Really?
Yeah, we only saw add.
Not okay, not necessarily the commands, but there's the registers and everything else.
Yeah, you have to know all the.
All of them.
Wow.
There's not a lot.
There-
Not a lot at all. So you have to know them. And you get used to it. The only way to do it is if you sit there, you guys should know by now for studying for computer science and computer engineering, like sitting there and trying to like read and memorize
It's not-
will not help you. That's not how it works. Also watching videos and like doing what other people are doing, like you watch it and just kind of type it out. You run it, it works, like yeah, it works, it feels good. You learn nothing actually. The only way to learn is to sit there yourself and actually struggle through the problem and solve it. It's going to take sometimes hours and hours. For debugging, you have to think about why it's not working. So one of the common problems we see nowadays is that people get stuck on a problem. Like in the old days, you didn't have a place to turn to. You had the instructor. But I remember going to my professor and said, it won't help you. They'll say, you'll never learn. If I show you the answer, you'll be like, oh yeah, that makes sense. And then they give you another problem, right? an application problem, not the exact same one, you can't do it. Why is that? Because you
You don't
didn't solve it
understand it.
yourself in the first place. It's a big problem that we have today, actually, in not just computer science, but in engineering in general. So you have to struggle through solving that problem, even though it seems like you might not know it. Given what you know, right? Like everything I give you guys to do, you should be able to figure it out, but only if you experiment and sit there and solve it. Right? Like if you learn nothing from this class, from me this semester, that's the one thing you should take away, is that you have to struggle through it. It's not different from biologically, actually. It's not different from doing any kind of physical learning either. You're trying to do some stuff, you have to do it yourself, right?
Mhm.
It's just the way we're built. Right? There's no shortcut, unfortunately. Otherwise, teaching, passing down knowledge would be so easy, right?
Yeah.
Although we may have something coming that may bypass that soon.
What do you mean?
We're
The
willing to
Neuralink?
embed a chip in your brain.
Would you do that?
Surgically, would I do that?
Yeah.
No.
Exactly.
I would not do that to my child either.
Yeah.
Yes.
So for the registers, we have register A, B, C. They usually like used for operations. Does that go on like to register?
No. The ones I showed you in the notes are, that's it. So
ABCD.
A, B, C, D. And then we start using the DISI registers for indexing. And then it's all R8 through R16, R15.
We can
Yes.
just do it.
Go ahead.
This is like slightly off topic, but like, let's say I wanted like a framework to start like building off of, because I'm a little unfamiliar with like, I mean, I can see like how x86 like relates to C a little bit, but I'm getting used to like exactly how to write it out. If I were to come up with like, kind of like a base framework to where I could start like adding more details in, like would I just start with the commands like move and add, push and pop, and then just like, and then how they interact with the different registers in the system kernel? Like you
So
gotta
this is it's a timely question because we're gonna start doing a lot of this today. I'm gonna walk through how stacks are used inside calling functions, subroutines, and then we're gonna jump right into an example that we'll do together on the board. And then you'll kind of see how to work with it and then how to inspect it using the debugger. And then once we're okay with that, next class when we come back, I'm gonna show you how to write assembly code alongside a C program where the main program is the C, but we're gonna write certain functions in assembly and make them work together. So that's one common way you'll find how people use assembly. And they usually do it because they're trying to get optimal performance for the application. So things that you really need to be optimized, we're gonna write in assembly. And then for the parts that we wanna just kind of get done, okay, for convenience, we'll write it in C. So I'll show you how to, we're gonna start doing that next week. But before we can even talk about that, we have to go through stacks and calling conventions and all that stuff. So that's what we're gonna try to do today. Okay? And by that time, by the end of today, you should be able to kind of see more of where things fit together and how to play with it. Okay? My hope is to leave you. You should be playing with this stuff already. Like last time, I asked you guys to check the endianness, right? For example. But really, by the end of the day today, you need to know how to write stuff and test it out yourself and kind of see how things go. Okay. All right. So obviously, anytime you talk about subroutines or functions or methods, you have to call it, and then the function has to return, right? So there's a call and a return instruction. We saw that even in LZ3. In x86, it's the same thing. The call function, the command, I should say, is there, and then the return command is there. What they do for you is that automatically it's going to save the return address onto the stack. Who remembers what a return address was?
A return address?
We did this in LZ3.
The address for the following instruction.
What's it?
The address for the following instruction.
Yes, it's the address of, so if you have a program, right? You're in your main part of the program, let's say. Like you're doing some stuff, and then you're gonna call a function, okay? Call function one. When it comes back, what is it gonna do next? Well, whatever the next line of instruction is, okay? So this is your main program, there's a function called, when you come back, you have to start executing code in the next line, right? Each one of these has an address in the memory. If you guys remember the program counter, that's what it points to. We have to save this guy's address so that we know where to come back to. Who remembers which register was used in LC3 to save that information?
It was R7?
R7 was used, right?
Yeah.
Okay. In x86 and other major architectures, they don't put it in the register, they put it on the stack. So on the stack, they're gonna take the address and save it. It's gonna push the address and save it there for you. So it's just gonna sit there. And when that function's done, and we call return, how does the computer know where to go back to?
It's already saved,
It's
so you
on the
just.
stack, yeah,
that's
top it off, and then it's right there. You don't have to do it. It's done automatically. And when it does it, the RSP register, the address sitting inside the register, will get automatically updated. It's all hardwired to do that. So that's all you have to know about it. You just call and then give it the name of the function, and then it'll jump there. And when you return, it knows where to come back to. So that's very convenient, right? So here's an example. Same thing, kind of like what I was trying to illustrate. When you call a function, right, it goes here, does a bunch of stuff, when you return, it comes back here, etc. Well, the first thing that you should think about is calling conventions. Caller save, callee save, these things, right? We talked about it. All of the stuff that we talked about in LC3 translate well into LC3. Sorry, not LC3, x86. But it's a little more complex, so we're going to walk through it one at a time. All right, in this example, we call this function called do this. So the computer will jump in here. It's going to do a bunch of stuff. And then let's say you push some values onto the stack because you're trying to save some information, you're doing some complex computation, etc. And then you forget to pop this off. And you leave it on there. And then let's say you try to return. What will happen? What's it? It will have an error. What kind of error? Any guesses as to what the computer might end up doing? By the time you try to call return, the computer wants to have on the top of the stack the return address. So that you know where to return to. Normally, it needs to come back here, right? But you put something else on it. So whatever that thing is, the computer's going to think is the return address. It will try to jump to a memory location that matches this value, some random place in the memory, and then it's going to crash. Okay? Yes.
I don't understand how, like, I know that the call function pushes the return address on the stack, but in which location is that address? Like, inside of the stack? The call function is pushing the return address
On the stack.
onto the stack,
Yeah.
and the return is
You're
gonna
gonna
pop
burn
it.
your rack.
Okay, where exactly is that location in the stack?
At the top of the stack. Every time you push, it goes on the top of the stack.
So the top, by the top would be this part?
Doesn't matter. Don't visualize. It's on the top of the stack.
Oh, so where the top pointer is?
Yes.
Oh, okay.
It pushes, it decrements the address at the top by one slot, so 8 bytes. Puts it there. That's it. So there's a problem. Any questions about this? Okay. So you have to be careful. All right. Take a look at this example. So I'm doing some stuff here. It looks like I was moving some data into my RAX register, and then I made a function call, and then upon returning, I'm also doing other stuff where it looks like I'm moving this data into RBX, and I'm probably continuing with lots of computation, etc. The question is, what happened to the value that was in RAX before the function call? And what do I have in RAX after the function return? Okay. Again, same issue we talked about in LC3, so you guys are familiar with this problem, right? Is RAX preserved by the function call? And whose job was it to preserve the value in RAX, if you care about it? Is it the caller, the main part, or the callee, the function itself? Because if you look at this function, I can tell you right away what's going to happen to RAX, what's going to happen to it.
It's gonna get.
Whatever you had in there is gone, right? It's going to get modified. And so the term for registers that get modified, and the values that are in the registers will get changed, those are called volatile registers for this particular function call. And sometimes when you write the function, as the function writer, your job is to kind of write that out, right? And describe which registers are volatile, because you're using it. And so whatever the caller had in there, the values are overwritten and gone. What's that?
Is it RBX?
It's nowhere. Because when you call the function, you move something else in there, it's gone.
That's after the call.
Yeah, and then when you come back, right, the main program is trying to grab the old value, it's not there anymore. Whatever we put there from this function is sitting in there, and it's wrong, or probably wrong, right? So we don't know. If you cared about it from here, what did you need to do? Save
Save it.
RAX somewhere else. Where's this somewhere else?
Any of them.
In the memory somewhere. In particular, a stack is how this is used. So you should have made a backup copy in the stack if you care about it. That would be an example of caller save. Okay, the alternate way of doing it was for the function, knowing, if you're writing the function, that you're going to mess up this value, and you have no idea if the caller needs it or not, right? Whatever was in there. If you want to be safe, what would you do?
Save it in the.
Yeah.
Yeah.
Before you mess it up, save it. And then after you play with it and you're done, restore it right before you return, and then you return. That would be an example of callee save.
Save.
Thank you. Right? Okay, you had a hand up?
Oh no! Is it? Nah.
Any questions about that? Okay, so these are kind of like review, right? So we talked about caller save versus callee save. And then we talked about, hey, how do we actually pass parameters into the function? And then how do we receive the return value from the function? And we use registers in LC3. We did that. You can also use memory locations, right? There's a lot of different ways of doing it, but you have to have some kind of a convention that you agree upon, right? That you follow, set of rules. The C language has a very specific calling convention that we're going to cover. We won't get to it till next class exactly. It's also been changing the way they do this. They used to exclusively use stack for both the parameters that go in and for the output values and different things, right? They used to exclusively use the stack, not anymore. They use some of the registers, and they also use the stack. And then to make matters more complicated, if you end up using any kind of floating point numbers, okay, how many of you have used floating point numbers in your Java, C, C++ programs? It's common, right? None of the registers that we talked about can handle floating point numbers. There are a special set of registers, XMMS, 1, 2, 3, 4, etc., that we'll have to talk about later. So for now, everything we're doing is non-floating point, okay? But we'll get there. There's also multimedia instructions and stuff like that help you do 3D graphics, right? Those also use different set of registers, all hardware implemented. Yeah.
Are there like registers for like just actually like true or false from like Boolean values or
No,
no?
unfortunately, it's all 64-bit.
Oh, okay.
All right. So here's how we did passing of the input parameters. You could use registers or the stack or both, right? The caller's responsibility is to make sure that correct values are in the location that you agreed on, right? Before the call instruction. And then afterwards, the caller would have to pop off all the values, okay, that you put on there after it returns. You don't want the callee to pop them off. Why?
Mm. Yeah.
Little thought question.
Because the calling as the values of the registers.
The registers, so in this case, when I say popped off, I'm talking about the stack. How's
Because
it done? Yes.
never mind, never mind.
Okay, well, let's keep looking at this and then we can talk about what the answer is. All right, so the C calling convention that we're going to start with, because we're only focusing on like integer type values, non-floating point values. The parameters are placed in these registers first, or in that specific order. So if you only have one input argument, you put it here. If you have two, you put the first one here, the second one there, etc. What if you have more than 6? Then you start putting it in, or on, I should say, on the stack. So let's say you have 10 parameters into the function. First 6 go here, and then this is what the stack would look like. The parameters are pushed in the reverse order so you can get them actually in order as you look at it. The return value from the function comes back in the RAX register. Can you have more than one return value?
Yeah.
You cannot.
Oh.
Not in C. You can only have one return value.
Mm. It's kind of crazy.
Any questions about this? Yes.
So after those registers are used, like to keep the parameters, they go into the stack, and then it starts at RSP, like RSP is like the
Where's the top of the stack? It's whatever the RSP is. It's always RSP. It's the top of the stack.
so the first value goes into
This is, what is this?
This is stack.
It's a stack.
Mm-hmm.
It's the result of having pushed
For
4 items on there and then having pushed the return address on there. And so now the top of the stack is here. Once this is done, if you are the callee, okay, so you're in the function, how do I access this 8th parameter?
you first have to remove this out, and
So this is where, if you pop this off, you have a problem, because I cannot lose this.
so you have to see
This is just memory locations, right?
Mm-hmm.
It's not an actual
Oh,
path
so you
displacer.
so
These
if
are
you
just
know the
memory. So
the
all I need
address
to
of
do
the
is
top.
access whatever RSP is plus 16, that gives me parameter number 8.
Oh.
And if I want, I can move that into any register I want, really. Maybe put it in R9. If you do that, it's gonna grab this value, put it in R9.
So that's a valid command?
What's that?
That's an actual working command?
Yeah,
Okay.
yes.
I'm confused about this. So, after we're done with 6 registers, let's say like the parameter number is 7, why does it go into like? Oh, okay, never mind. I got it. It's because I was like thinking about this once, like about this, like this one it would go like where the parameter number 7 would go into where the parameter number 10 is. But I understand that's because of the pointer of the second one. Never mind, I get it. Thank you.
All right, so let's take a look at an example. Any questions about this? We're gonna have to come back to the C calling convention because we're gonna use it. If we're using both assembly and C, we have to follow the C calling convention. Does that make sense? Because when you compile it, the C compiler will expect you to be following this thing, otherwise it won't work. But if we write only assembly, and we're only staying within assembly, and I'm not interacting with C, I don't have to follow C calling convention, I can do whatever I want. So let's say I'm just gonna use the stack, like they used to in the old days. And I'll show you an example here. So in this code, I've got 3 like variables, right? Defined like this. And then, let's see if we can read all this here. So here's my function, it's called do that. And then here's kind of like my main part of the program. Okay? So what happens is that I'm gonna take whatever is at this location, grab what? The value at that location. When you put this bracket around a name or an address, it's actually gonna go there and grab the value at that location. So what do we get when I go here? It's a 7. So it puts the 7 in EAX. Therefore, how much information did I move?
4 bytes.
4 bytes. Why? 4 bytes. What's that? How much did I move? How does the computer know how much to move? It's the
E?
It's the name of the register that tells if that's the hint. And it's the only hint that we have, the computer has. You're telling it to move some data into a 32-bit register. And so it's going to move 32 bits of information located at wherever this is. Okay? How big is my data?
Like 3 bytes?
DD is what?
DD means
4 bytes.
4.
Yeah.
Okay? So it was in 4-byte format. So I moved it there into EAX. Does that make sense?
Yeah.
Okay. Now I'm going to take the entire RAX and push it on the stack. Why?
You want to store that data?
Is it?
You want to store that data?
I'm going to put it on the stack because I'm going to pass that in to the function as an input parameter, basically. That's what I'm doing. Well, why did I put RAX? Why didn't I push EAX? Who remembers? From what I said earlier. Why can't I push EAX?
Does it not work?
The stack only works with
8
8
bytes.
bits, 8 bytes,
8 bytes.
64 bits. So I had to move the entire thing. What's in there?
There's a bunch of zeros and then at the end
Bunch of
there
zeros
is
and then 7. Yeah, that is right. Are you guys okay with that? Okay, so we pushed one item on the stack. Yes.
For 32-bit systems,
Yeah.
is it 4 bytes for a stack? Or
Yes.
is it-
All right, so next I push onto the stack data 2. So this time, I don't have those brackets around it, right? So what I'm asking the computer to do is grab the address. If you don't have brackets around the name, it's going to assume it's an address. It's going to grab the address of this variable and push it on the stack. And then I make the function call. So at this point, how many items did I put on the stack? Two things, right?
The
And
actual
then
set.
when I call, it's gonna put the return address on it. So as a result, this is what I'm gonna have in my stack, or on my stack, at the time of the function call. The first item that I put on there is my actual data from data one, the address of variable called data two, and then the return address. The top of the stack is where?
The top is at RASP.
Always at RSP, right? Always at RSP.
When you say return at, sorry, what does that mean?
It's a return address. Okay. Return address.
So the return address is the address that you have.
Probably from this line, whatever that is. Immediately following the function call.
So what's the RSP is the return address?
Yep.
Um,
It's always like this on a function call. Top of the stack will have the return address. So now we jump into the function call. What does it do?
It moves.
What is that?
It moves.
Grab RSP plus 16. What are we
It,
gonna get?
it grabs the. It grabs data
The
one.
value
Yeah, the value.
7
7.
Yeah. And puts it.
Put it where?
R.
RAX.
Any questions about that?
No.
That's it. Next line.
And then it grabs the add. Oh.
Then it grabs the
The address.
address of what?
Of
Of data two.
Yeah.
Data 2.
Then it moves into
It's in
RBX.
RBX. And then what does it do? Next line.
It like gets the data RBX and then it adds it with the data value of EAX. And then it returns.
Well.
I mean,
Oh,
it's adding the
RBX
brackets.
is in brackets, so
Yeah.
it's the value number 3.
Yeah.
We're looking at this place right here.
Yeah.
Yeah, so it's 3 plus 7.
Why EAX? Why am I not doing RAX?
Because
These things are 32 bits long, right? So when I go to grab this guy, it's 32 bits.
yeah.
I'm trying to add 7 to it, 32-bit version.
Oh, so you need to
So
keep.
we say EAX, right? You gotta be very careful with this stuff.
Mm.
Okay.
And then where's the result gonna go?
It should be 10.
What's it?
It should be 10, the return value.
The result, where's it gonna go? This added
It's
instruction
going to be R to
here.
RBX, to the value, to the register RBX.
Yeah.
This variable is gonna change.
Oh, it's going to change in there, data 2.
Look at this, the way this is written.
It's because the source
Where does
destination
the
is
add
RBX.
instruction put the result?
In RBX.
In the whatever is left side, right?
Yeah.
That's the target location. We're gonna try this out, see if it actually works. This is what you should be doing. After we talk about all this, when you go back, when you try to study, this is exactly what you should be doing. You should type this out, explore and play with it step by step, and watch the registers. If it doesn't behave the way you think it should behave, you gotta figure out why, right? If it behaves the way you think it should behave, great, right? When we return, what do we get?
We get 10
We should be
or-
getting.
There is no return value.
Wait, RET.
So I just come back.
Oh.
And once I come back, I have to pop off or get rid of the items that I put on the stack.
Mm.
So I simply take the RSP and add to it 16. You add 8 each time you push one item on there, right? To get rid of it, to undo the decrement.
Um.
So this is how you actually do it. You don't actually pop. You do this?
Hmm.
Why don't we do the pop? What if I had 50 items I put on the stack?
You
gotta
would have to
pop
do pop
50
50 times.
Wasting time, right?
Instead of that, you can
And
just
change the address of the stack.
address. You just move it. The 16. Oh, so you move the address above the data one right there, right?
Yep.
So you just move it up there.
And then I'm gonna take whatever is here, load it into EAX. At this time, in my debugger, DDD, I would look at the content of my RAX register and see if it's actually 10. If it is, this worked. Does that make sense?
Mhm.
Can we?
Where did I store the result of adding the 7 and the 3?
That's
I saved it here. This is in memory, actually, somewhere in memory. I got 3 variables, and I put it here. The result, 10, didn't go through the stack. I didn't return the value from the function. I simply modified the original memory location. And the way I did that is by telling the function where it's located. I gave it the address. And we use that location directly in the function. All right, so here's I'm gonna work with the same example. Now what happens when I do this? What do you think will happen? It's now a 64-bit addition. And so it's gonna grab
32 feet.
7, right? The 64-bit version, so there's a lot more zeros in front of it. And then it's gonna go here.
But
And it's gonna grab, starting from that location, it's gonna grab a 64-bit chunk
Which would
and
occupy
then
the.
add this to it. So what is from here 64 bits of information?
Up to the
This
lower
one plus
and
probably
that
whatever
one.
comes next is gonna get grabbed and chunked together. And then you add to it RAX, which is 7. Is that the same thing?
Oh, no.
We're gonna have a problem. When you run this in DDD,
Will it-
you want to do this yourself and see what happens to this data. Okay? That's how you learn how these things work. I want to see it. Okay? So I'm going to show you how to get that. So this was an add operation. What if it was an AND operation? How would that change things? Right? So I want you to see it happen. Okay? All right. Next, same exact setup. This time, I'm coming here and I'm saying, hey, I'm gonna load these things, right? This time I'm passing in both the addresses for both variables. And so I'm gonna load those addresses and I wanna do something like this. But you can't. So I have to do it in 2 steps. Why can't I do this? Well, let's say this is allowed. So what is RAX brackets? Well, RAX was pointing to this thing, data 1. This would be data 2. So I'm asking the computer to go directly to the memory locations of these things, grab them, add them together, and save the result in here. It's not allowed because it's a memory to memory operation. You cannot do memory to memory operations.
You have to bring it to the register.
One of them has to be a register, at least one of them. So instead, I load it into a register, and then from the register I get. So it takes 2 steps. Any questions about that? All right. So now, let's say I want to create some local variables inside the function. How many of you have done that? when you wrote a function, you had some local variables, part of the function. Who has no idea what I'm talking about? Local variables. What is a local variable? Let's say I'm inside a C program. It doesn't matter what language. Since we're using C, I'll say C program. Special function, okay? Takes in, let's say, 3 input parameters. And then we're supposed to do something here. Inside this function, I don't know, I need variables, you know? Answer, X, Y, etc. So how many variables did I create inside the function? 5, right? Those are called local variables, local to the function. Where do these go? Anytime we have a variable in a program, we need a place to save this. Where is it? Are we going to use registers for these? The answer is no. Sometimes you can get away with it, most times, well, often you can't. Because you need the registers for like actual adding and counting and all that stuff that goes on. You don't use registers. So it has to go in the memory. Where in the memory? If you remember like LC3, I had to specifically make like spots for it, right? I can't do that for a big program every time I write a function. But I need local variables. So the answer is we create room for these things on the stack. How do we do that? Well, look at this. I already created space for 5 elements on the stack. There's no value, right? So I can't push anything on the stack. I'm not pushing anything on the stack. So how does it work? This is how it works. Inside the function, as soon as the function is called, right? Right when you start the function call, this is what the stack looks like. You have the input parameters like we did before, and then the return address is at the top of the stack, right? Any questions about that? Okay, I want to create space for 2 local variables in this example. What do? I subtract 16 from RSP, which causes the stack to look like this. What did I just do? I created 2 things on top of the stack, on top of the return address. And this is now what my stack looks like. What's in here? I labeled it local variables, but initially what's in here? As soon as I do this, right? What do you think is in here? Nothing. You can't assume it's 0, because there may be some garbage still in there. Nothing is the answer. Just some random stuff. I shouldn't say nothing. Random values is the more accurate answer. And then I can start adding things in here as I need it. So you want to create a variable sum that keeps track of the running total sum, right? I need to initialize my sum to 0, right? What do? I know I have to put 0 in there. I'm going to say, hey, I'm going to use this as my sum. So you use that as your sum. You always refer to RSP plus 8 whenever you access the sum variable. Does that make sense?
And then our SP will be 0.
Which one?
You said that the plus 8 will become 0?
Yeah, this part will now become 0.
Yeah,
when I do
okay.
this.
And then you can start.
So you access the stack directly without using the push and pop. Because I'm not trying to put stuff and take stuff off there. I just want it to have a place on the stack where I kind of use it as a space for variables, okay? That's what's happening. So you directly access the stack this way. When you're done with this function, I need to put if my stack looks like this, okay? And I say return, what happens?
Well, it will return.
This would be like a
not-
good exam question.
You,
Maybe a picture of the stack.
it's returning
This
now.
what happens. If I call return, what happens?
It's not returning
Should we
anything.
return RSP position?
It's gonna assume that the top of the stack, which is where RSP is, has what in it?
The local variable one.
The return address. But it doesn't. Does the computer know that? So what is it gonna do?
Just grab like a
It's gonna
range.
try to go there. We saw this in LC3, right? It's gonna go there. Whatever this value is, it's gonna think it's a memory address. Try to jump there, probably just crash. 99.9% of the time, it's gonna crash. And that 0.0001% of the time, it's gonna land you in some random place in the memory, and you might get lucky in some instruction. But it's not your program, it's some random place, okay? Almost never, it's gonna crash. So I have to restore my stack to look like this before I return. How do I do that? I subtracted 16 from RSP to make it like this. So I add 16 to RSP back to this picture. Any questions about that? Okay, let's play with this stuff now. I've uploaded a assembly file that we're gonna use. And we're gonna do first, we have a value, an array of numbers. I'm gonna find the total sum of all these values. Once I do that and it works, I'm gonna figure out how many negative numbers are here. And then once I figure out how to do that, I'm going to make a copy of this into another array where I copy the absolute value of this stuff into that array. What is absolute value again?
We just do the two.
Positive magnitude only, right? So it's going to convert all the negatives to positives. Put it in the other array. That's what we're going to do. And then once we're done with this, we're going to do the same exact thing. I'm going to have you work on this, but you're going to write subroutines to achieve the same thing that we're going to do. So you're going to have a function called sum that takes in certain things and outputs certain things. You're going to have numneg that does certain things, etc. But let's do it inside the main part, one at a time first. Okay. What is the sum of all these values? I made it easy.
0? No.
I didn't want to do 0 because when you see that 0 in the register, you're not sure that the 0 is there because we did the calculations correctly, or if the
because
0 is just there, because it's one of the most common values, right? So these all cancel out.
Just see.
It's 7.
Mm.
T minus 8, it's 7. But we should see it update the total sum as we add, because it's going to start at what? -8?
Mm.
When you add 3, what does it become?
Negative
-5.
5. The
-4. -9, right? Like that's what's gonna happen. You should see it like that. All right. Oh, I think it's working. Let's see. Maybe not. It got a little bit bigger thing really doesn't like my font size. All right, doesn't matter. Let's do this. All right, where's my program? Did you guys download the program? Okay, I'm gonna open my assembly file. Look at it. Looks like this. Okay, so let's talk about it. This is the solution. To the summation problem. Do you guys see it?
Mm-hmm.
Tony, can you see?
Yeah.
Alright. So here's my array. Initialized values for variables go in the dot data section, so I did that. I also created space for the other array that I'm going to eventually copy to. 10 spaces, queue size, right?
Mm-hmm.
So I did that. And then here's my code section. In my code section, you can see that I'm using RAX as my sum, total running sum set to 0. I'm using RCX as my counter. Okay? And then what I'm doing is I'm actually loading the number. So I asked the computer, hey, go to this location plus, because each item is how big?
It's quad, so it's
Queue size, so it's
So it's
8 bytes.
yeah.
Okay, so each item is 8 bytes. Whatever the address is, this is stored at that address, this one's stored plus 8, plus 8, plus 8, right? So 8 times the counter. In the beginning, counter is 0, and therefore I'm just looking at here. When the counter goes to 1, it's going to be nums plus what?
times 1.
1 times 8 is?
Yeah, is 8.
1. So plus 1, 8 there. The counter is at 2, what is it?
So
Plus
times-
16,
Yeah.
which means 8, 16.
Mm.
So this is how you access arrays. We covered this last time, right? Any questions about this? So I'm having the computer go to this location, grab the value, and put it where?
RDX.
RDX. And then what do I do here?
You add or
Add that value I just loaded into my
RDX.
total sum. So this is like what I'm doing, basically.
Mm.
Any questions about that?
No.
It's pretty straightforward, right? And then what do I do? Well, I have to increment my counter. And then once the counter reaches 10, I'm done, right? So if the counter is not 10, I go back here and loop.
Mm.
Is what's going to happen. Once it reaches 10, it's just going to come here and this is all exit stuff. You don't have to worry about it. This is how you properly exit from an assembly program.
Mm.
Where do I see the value?
You
there is
didn't
no print. We don't have
print.
print. We don't have it. We don't know how to do it yet.
you just sum it and store it.
Yeah,
or
just stop it
yeah,
here and
stop.
we can look at which register
Or yeah.
or AX would contain the values. Any questions about that? Yes.
Can you explain what the section dot BS?
Yeah, this is telling the computer this is the code.
Yes, section, yeah.
Okay, that's what
And
this
this section dot BSS. What
This
that
one
means?
is uninitialized data.
What
Mm.
it means.
Like I created an array, empty array.
That's just saying you create an empty array with 10 spaces.
Size 10.
10 size 10.
And then data is initialized data.
Initialize data.
Interestingly, a lot of times, these get put in the same location, same section in memory, but that's up to the operating system to decide. We separate them in assembly like this, and it's up to the OS to decide
So we
how they
don't
manage.
we don't tell which line it goes in. So Charles,
Any questions about that?
uh,
Let's compile it, let's actually run it. Who remembers how to compile this thing, or assemble this thing? NASM is
Yeah.
correct. So, I'll do like this, NASM, and the name of this is, what do I call it? Lecture 13.asm. Once I do assembly, I do next one.
That's right.
Link it. And then lecture 13.0. Done. Now I'm gonna go to my debugger and I will load it. And there's my program. I'm going to put a pause at the beginning of the program right here. So I put a breakpoint right there. Okay, so I put a breakpoint right here. Any questions so far? What's it? I just double clicked on this one. You can also right click to disable and enable. When I run, it stops at that line. So down here you can see it. So here's the source code. Here's the machine translated version of it. Because we wrote the code in assembly, it's going to be one-to-one, basically. So it says, my code here is move 0 to RAX. The machine code says move 0 to RAX.
But it doesn't
Why?
explain that.
Why do we have the same thing? It's the same thing. Trivia. It's the same thing, because I wrote in assembly, it's the same. What if I didn't write in assembly and I'm debugging a C program? What will I see here? C code, and then here you'll see the assembly. That's why. But we're doing assembly, so it doesn't matter. Yeah.
When you put a breakpoint, it stops in like before.
Before it executes that line. Yeah. Any questions so far? Good. When you look down here, you might get confused because it has different kind of like notations for the same thing. And the ordering of the operands are like reversed. It's because this is using GNU syntax. What we're doing is, what we're using is more like Intel syntax. So, don't worry about it, okay? There's a way to change it here. But I'll just leave it for now, because we're gonna look at our code here. All right, so I'm gonna go look at my registers. So I open up this window that shows the values in my registers. How many of you have like really good vision and can see this from where you're sitting? You can see it?
I didn't read like the summary, so yeah.
Okay. Can you guys see it?
A little bit.
A little
Most
bit?
of
You
it.
should move up, because we're gonna need to see it. So like slide your chair
Oh.
up here. And
how did you
watch it.
open the registers?
You go to the status menu and there's the registers. So I'm gonna leave this open like that, okay? I'm gonna hit next. It moved 0 into RAX. We don't see a change because it was already a 0. That's fine. And then it's gonna set ECX to 0 next. Again, you don't see it because, why? It was already 0. So now we're looking at the next line, which is moving the data. So this line right here, big text. Now we're here. the result of this operation, if I hit next, what do we expect to see inside RDX? Well, it's the first time around. So I'm gonna grab this guy, and it's gonna go inside RDX. My RDX right now is what? 0. What do I have? -8. Is that correct? It did exactly what I just said it was going to do, right? Okay, next line, it's going to add the -8 into my running total sum. Which register is being used to keep track of the running total sum?
A RAX.
RAX. Any questions about that one? About why I did it? Because I made it that way. You have to pick some register, right? So I picked RAX, and I'm adding it into RAX. So the result of this operation should be that I have 0 plus -8, which is -8 in RAX. There it is. And as I flip through, all the numbers from the array should be added to this register. I'm going to next increment my counter, so our CX is going to go to 1. You guys see that? Any questions about this? Okay with it? Next, it's going to compare RCX against the 10, and decide to jump or not. So it jumped. Now we're going to go next. Load the next value into our DX. So I get 3, is that correct? Well, look at the data. Correct. It adds it to -8, so I get -5. Just keep going. 4, 9, 1. You can see the counter, we're at 8, 9th value. There's my final add. What is the result?
7.
Is that correct? Any questions? Okay, so at a bare minimum, I gave you this code. You should be able to do what I just did. If you can't do it, we're going to have a big problem because you won't be able to do anything beyond this point. So you need to be able to sit there, repeat this experiment. What does it take to repeat this experiment? What does it take?
Not doing it.
It's just nothing. Just do it. I can't help you if you don't do it. I gave you the code, right? So the next part, we're gonna do it together. So I'll help you even more, right? We did this part. Let's figure out how to do. How many negative numbers are there? How do we do that? So let's take this code and think about it.
Well, the numbers that we are loading from the array is being stored at our
Right here.
DX.
RDX. Each time I load the next number,
It goes to
It's
our
RDX.
DX
so I have to inspect RDX
and see.
and see if it's a
Before-
positive, negative, whatever, right?
Yeah.
So, and we could do that. The summation is not affected by what we're about to do.
Mhm.
Because regardless of whether it's positive or
What
not.
the result,
I'm
it's not
gonna add
changing
it,
the
okay?
our DX.
So I'm just gonna add an instruction, in here somewhere that decides whether or not RDX has a negative number. If it's a negative number, what do?
If it's a negative
I
number,
keep track of
you
it, so I'm probably
add
gonna need another
counter.
counter to count each time I see a negative number, right? How do I keep track of that?
Branch?
What's it?
A branch?
Branching is how we're gonna, well,
check if
It's
it's
comparison.
Yeah,
comparison.
so that's all gonna go in here, right?
Yeah.
See,
I need a variable or a place to to keep track of the count. In the beginning, how many do I have? How many negative numbers? Before I checked anything, I don't know, so it's a zero.
Zero.
Yeah.
But each time I see a negative number, I have to increment it
By
By
one.
So what register should I use for that? What is it? You could use any register that we haven't used, is the
Yeah.
correct answer. RDX is a good one, right? I could use any of the numbered ones, like, yeah. So we could do that. We haven't done that, so we can try. I would do it here. Why? Because this is part of my
Where-
loop. I cannot initialize variables
Yeah.
inside the loop because it will reset itself every time, right?
Uh-huh.
Mhm.
So before the loop, right here, I would, let's do it. Let's pick one. I'm gonna do R15, how about that?
Mhm.
0. And this is a number of negative values. How's that?
Mhm.
Any questions about that?
No.
To say, I'm gonna do right here. Figure out if this is a negative value. How do I do it?
Well,
It's a comparison.
mm. Hold on.
Where's the data?
In RDX,
RDX, that's correct.
compare.
And comparing it against
Um,
a 0, if it's less,
yeah, if it's less than
Right?
0.
I know it's a negative number, right?
Mhm.
If it's not, if it's greater than or equal to,
You don't
then
want to
it's
do it.
not a negative
Yeah.
number, right? And using that, I can do whatever I want.
So,
So,
right, right?
I'm gonna do like this. Let's call it PZ. If it's 0 or positive, I leave it alone.
Mm.
Otherwise,
Otherwise, if it's just negative, you would add 1 to R15.
I have to count up. What am I counting up? R15.
Yeah.
How many of you like this?
Yeah.
How many of you like this?
Yeah.
Either one's fine. We're done. At the end of the loop, okay, RAX will contain my sum, and R15 will tell you how many negative values it saw. Does that make sense?
Mhm.
Any questions about that?
Nope.
I'm gonna save it. Let's run it. Because I could be making mistakes, right? So let's reassemble, relink, and then I'm gonna reload it here. And then instead of stopping it here, I'm gonna stop it at the very end. So like right here.
Mhm.
Okay. So we just see the result. So I'm gonna run it. What do I expect in RAX? It should be a sum, so 7. In R15, what do I expect?
Well, just
Come.
Is it 5? 5 negative numbers?
1, 2,
So I ran it.
4, 5.
Sum is correct. R15 says
5.
5.
1, 2, 3, 4,
Did it work?
5. Yep.
Mm-hmm.
Beautiful. Works pretty good. Okay, last part. Copy absolute value into another array. So what I'm asking here is that I need to take each number, convert it to the positive version of it, and put it here in the other array.
Okay. So,
Okay? So
I mean, You can do some ASCII
I
stuff.
probably need to do something similar because I gotta know if it's
Yeah.
positive or negative, right?
Mm.
If it's negative, so negative.
You know, to use the operation that, is it negate?
If it's negative, so right here I know it's negative, right? Because I'm
Yeah.
counting the negative values.
Yeah.
I'm gonna convert it to a positive version. There's an operation called MEG, right?
Mm.
It flips it for you. Look how convenient that is.
Mm.
Now what?
Now would try using load. We have to.
Well, actually, I shouldn't have flipped R15. Everybody was like nodding. What would that have done?
You've -5 now for your number.
That's my
Yeah.
counter,
Yeah.
so this is no good. Which one should I have flipped?
You should flip.
RDX, thank you. Okay, now that I've done that, by the time I get to this label, RDX is always a positive number.
Awesome.
Now I can take it and save it in my array called RSLT. Okay, how do I do that? Well, it's the same as this, really. But the direction of the information is
Is
reversed,
opposite.
right? So I'm moving from RDX, right? Whatever is here now, it's
Mhm.
gonna be a positive number. Where do I put it? Into this location plus 8 times the counter for the correct offset. This is your index. Okay?
Mhm.
Here's the name of the array. Here's your index value.
Mm.
Again, we talked about it last class. Just as a reminder, that's how it works, right? So if you write in C, like this is the name of the array, and I want to access, let's say, the 5th element, what index number do I use?
If we're actually
5th element.
we would use just 5 times.
No, in C.
In C is the fourth.
Or in Python, whatever.
Yeah.
This is what we're trying to do. In assembly version, it is RSLT plus 4
Plus, oh.
times the size of the data that we're working with, which is
Oh.
8
8
bytes.
bits.
Okay,
Oh,
that's
that
what
works.
this is. Imagine how much fun you guys are gonna have when we hit matrices in a couple weeks.
Thanks.
With 2-dimensional arrays. There is no second index. It's all linear offset based on the starting address of the data.
So wait, with 2D, with no 2D arrays, there's 2 indexes, but with this, it's just 1 index, but it's like 0, 1, 2, 3, 4, 5, 6. It depends on how long it is,
Yeah.
but the indexes don't change. It's all. Oh wow.
But you have to do the conversion.
Okay.
We'll get to it. Was it? Yeah, that's it. That wasn't so hard, right?
No.
Now let's try it out. Okay, rebuild the program. I'm going to reload it. I'm going to remove this whole breakpoint. I'm going to put it back here. Actually, I'm going to put it right here. That's the line where I'm actually storing each converted number or the positive number into the resulting array.
Mm.
So the problem with this part is that I can't see the result, right?
Mm.
Because this only shows me what?
Registers.
Registers. So I have to have a way to look at memory location.
Mm.
And this is where DDD is great, because I could look at memory location. The way I do this is by figuring out the address of my data that I'm trying to track. So I would like to know what happens to this guy, right? RSLC. That's the variable. So I need to know the address of that thing. The way you do that is by asking the computer to print, okay, so print address of RSLT. I don't know if you guys can see it, but I type print %, RSLT. Make sure you remember this, because you will need to know how to do this to do anything with programming in x86. If I hit enter, or when I hit enter, it gives me the address right here. So I have it, it's 402050 in hex. So now that I've got the address, I'm gonna go here and ask the computer to track the memory location. And I'm gonna say, hey, there's 10 values in hex format, each 8 bytes long, at location 0x402050. Okay? You guys want to take a picture of this? Take a picture of this. This is how many, how big each, and then starting location. All right, I'm gonna say display, okay? What change did you guys see?
The little display pop up.
Right here. That is my array in memory. It's zeroed out actually. All right, so it's running. So I run, and the code is waiting for me here. I'm just gonna keep running it. Each time, I should see a value copied into this location. Right? What do you see? It's 8. And you can see the highlight. You see the change? You see yellow?
Yeah.
That tells you something changed in that place.
That's 8.
Okay, so there it is. And then keep going. You see change?
Mm-hmm.
Okay, where are we at? Can you guys read that? How many values have I copied so far? Four of them, right? It says 8315, is that correct? So we did, where's my code? We did these. So negative number's been converted, positive version of it, so keep going. So there's my 2, 2, 5, 1, 3, F. What's F? What is that? 15. Oh, yeah. So my array, this thing, now has all these values, the positive version. Yes?
So what is the R for the 15?
What is R?
Yeah, like in the
Here?
actual code, no, in the actual code.
This one?
Where you have the where you have
Line number.
wait, you mean so I can't find it now. Oh, okay, yeah, here, the nums. The
This
num
one?
stack, yeah.
Yeah.
There's an R nearby.
What R?
After 15 there's an R. Isn't that an R?
This?
Yeah.
That's not an R.
What is that?
Every line has a little weird character in there. If you notice, every line has that little,
Oh.
it just means end of the line.
Oh, okay.
Yeah, it's something wrong with the font face. All right, any questions about it? How do I do this? Now I'm using subroutines. This is what you guys will have to play with. I'm gonna leave this code and upload it for you, the updated version. So I'm gonna put up the original ones already there. I'm gonna give you the one with everything in it, so you have both versions. You need to go back and try to recreate the full version from the initial version yourself. If you can't do it, you're in trouble, so you should come and ask me questions. If it's not remedied by next class, the problem's gonna get compounded because we're doing more complex stuff each class. You all have taken CSC 160, and we'll know how this goes. And if you get lost on one thing, there's no catching up, right? It's gonna go pretty quick once we start doing stuff. And by the time we get to matrices, and we're gonna take like pictures in BMP format, load it into assembly, and like manipulate the bits, flip pictures around. It's gonna get really bad if you can't do simple manipulations. Yes.
So we're taking pictures.
We're gonna take a photograph,
Okay.
load it, and it's a matrix data,
And
two-dimensional matrix, and we're gonna
that's
manipulate it.
that's cool.
Yeah.
And all that assembly code we're gonna somehow manipulate it to actually like pop out the picture. It's like it's a
I'm probably gonna have a photo of a pizza,
yeah.
and then we're gonna flip the pizza.
Oh no, we're flipping the pizza to the left.
Yeah.
Oh, we're like flipping the pixels.
Yeah.
Like each pixel is like a little bit of
Matrix.
code. Yeah.
All right, any questions?
Is there like, well, I mean, by no, nothing. I mean, the subroutine would be just like calling, just separate what we just did, this program that just gave it to us. We're just going to separate that into different functions. We're gonna show the like, oh, function one will do the
That's right.
sum.
You do it like this, right?
So the program is okay. We just need to pass it the parameters into
Yes,
each function.
into the
That's
stack.
that's the
exercise.
Okay. The program is already there. We can just copy it, right?
Yeah, I already uploaded.
Yeah. I mean, we can just use the same program.
Yes.
And just add the functions to it.
Yes.
Okay.
You're practicing what we did in lecture today,
Mm.
basically. I'm breaking it down like this for most of the stuff because I realized if I don't give it to you like directly like this, a lot of people are not working on it at home. You should be spending time, right? We talked about it. NCC standard is like 10 hours a week outside of class.
Mm.
And if you're not getting it right away and you're not putting in 10 hours, you're going to have a big problem. So I'm going to upload this. 1 second.
Maybe in the just don't you.
All right, any questions? Okay, you guys have some work to do, yes?
And when you're for the NASM command, I saw you put in capital F and then stats.
Yes.
What does that do?
So this part, pull it up. This part. This part inserts information that the debugger uses to track where things are. So for you guys, for my own computer, I use, is this what you're doing?
No, I wasn't even including the capital F at first.
So I use the Dwarf format. And that might work better actually. This computer has like some old stuff that I couldn't address last
Okay.
time.
For DDD, what type of NASM do you use?
What?
For DDD, what type of NASM do you use? Because it's difficult.
It's the same command that you use.
But on your side, so the different command than just for
GDB is DDD.
Is it the same thing?
Yeah, GDB is what's run behind DDD.
Yeah.
DDD just is the GUI for it.
So
If-
just use that command.
If you don't install GBD, you won't be able to use DDD. It'll give you like
if
a
you
little.
install DDD,
Yeah.
GDB is already there for you.
Oh, well, last time when I installed DDD first, it says you do not have GBD, something like that, and then I had to like install it.
That's possible, depending on your computer.
Yeah, my computer's a weird one. Yeah.
Using Dwarf fixed the issue I was having with opening the file in DDD.
What happened?
Well, I tried using stabs and it wasn't opening the file right. But
Yeah,
I just used
Dwarf is better, right? So for most computers, Dwarf will work. That's what I use on my computer.
Okay.
This computer is just got some weird issues, and I'm gonna try to figure out what fonts are available so we can enlarge the fonts. I got it to enlarge a little bit today, but it's not.